At this point, you should be familiar with two types of chemical reactions. You know what a synthesis reaction is, when two simple reactants come together to make one more complicated product. And also what a decomposition reaction is, when you have one complicated reactant that breaks apart to make simpler products. Those are the two most basic types of the 5 types of chemical reactions. Today we're going to learn about 2 more types of chemical reactions, as in this lesson we explore single and double replacement reactions. Once again, remember, these are the chemical reactions that are causing all of the changes to bonds in atoms all around us every single day. And understanding these different classes of reactions helps us to get a better understanding of what's going on with real-world substances everywhere. Let's get started learning about single and double replacement. And we're going to start off with a definition of a single replacement chemical reaction is one where you have an individual element. And remember what an element is. An element can be a bunch of individual atoms. It could be a group of atoms bonded together as a molecule as long as all the atoms are the same kind. Or it could be a group of atoms bonded together in a crystal as long as all of the atoms are the same kind. So we're talking about one type of atom, an individual element, okay? You also have a compound, a substance that's multiple types of atoms bonded together in some way. And what's going to happen is that individual element is going to bond its way into the compound, and it's going to kick out one of the elements that was originally in the compound, so then that will be by itself. Now, that was a mouthful. Let's take a look in pictures what's going on in a single replacement chemical reaction. And the chemical reaction we're going to look at is quite an interesting one. This is one that NASA is planning on maybe someday using on the moon, where we can take iron oxide or rust on the moon, heat it up, wash over it hydrogen gas, and what happens is the oxygen lets go of the iron that it's bonded to and then combines with the hydrogen to make water. Do you see why this would be a useful chemical reaction on the moon, where there's plenty of iron oxide but not a whole lot of water? Let's take a look at what this chemical reaction looks like. First of all, we have iron oxide, okay, which is an iron bonded to an oxygen. And then also we have the element hydrogen gas. Now, this is H2. It's 2 hydrogen atoms bonded together, but it's still an element because it's just one type of atom. Now, iron oxide doesn't look just like this. Iron oxide actually is a crystal, so I'm going to make it look like a crystal. And then watch how this reaction proceeds. I'm going to keep the iron and the oxygen next to each other for just a moment, and I'm going to move the hydrogen down, but I'm going to break the bonds apart because that's what happens during a chemical reaction. Notice all of the bonds have now broken apart. Here's how this chemical reaction is going to proceed. Do you see how the iron is next to the oxygen, the substance that it started with? Well, what's going to end up happening is the elemental hydrogen is going to move in and kick the iron out. And the hydrogen is going to replace the iron in the compound that it once made. So what we're going to end up with is, instead of iron oxide, we're going to have water molecules, and the free element at the end is an iron atom that's ready to bond together with other iron atoms around it. This reaction makes water and pure iron. All right, now let's just check and make sure that we did everything right in this reaction by looking at the substances we started with and making sure we have the same number of atoms before and after. I have 1 iron atom on the reactant side and 1 on the product side, 1 oxygen atom on the reactant side and 1 on the product side, and then 2 hydrogen atoms on both sides. This is a balanced chemical reaction, even without adding any coefficients to it. This was a single replacement reaction because the element hydrogen bonded together with the crystal iron oxide. It kicked out the iron from the crystal and became hydrogen bonded with oxygen, which is water. And then the iron, which originally started off bonded, was a free individual substance, an elemental substance at the end. That's single replacement. Before we move on to the next type of reaction, double replacement, let's just take a look at a few more examples of single replacement reactions. In this one, aluminum combines with copper chloride to produce aluminum chloride and free elemental copper. I just want to make a point as you look at this chemical reaction. When you're trying to figure out if it's a single replacement or a double replacement, don't look at the subscripts. The subscripts don't really tell you what's going on with the materials in the reaction. It just tells you how many atoms are involved. Look at the actual elements, the symbols for the elements. In this case, you can see we have a free aluminum atom at the beginning and copper chloride bonded together as some kind of a compound. In this case, it's a crystal compound. In the end, the free aluminum element bonds together with the crystal and kicks out the copper. So we end up with aluminum chloride crystals and then free copper. When you have a free element at the beginning and a different free element at the end, chances are you're dealing with a single replacement reaction. Check out how these other two reactions also fit that same pattern. Do you see how there's a free element at the beginning and then a different free element at the end? That free element at the beginning kicked out a substance from what it was bonded to in a compound? That's single replacement. All right, let's take a look at what double replacement is, because if you're still struggling to understand single replacement, looking at double replacement might help you to understand. In a double replacement reaction, you have one element in a compound and another element in a compound. So you have two compounds to start, and the compounds are actually going to switch one of their elements out with each other. All right, let's take a look at what that looks like. Here's a double replacement reaction equation where we have sodium fluoride and hydrochloric acid producing hydrofluoric acid and sodium chloride. You could almost hear the double replacement in what I just said. But let's take a look at visually what this looks like. Here's a sodium fluoride unit, and here's a hydrogen chloride or hydrochloric acid unit. Sodium fluoride is a crystal compound, so I'm going to separate it into its crystal structure. And then we're going to bond these two substances together. But to do that, all of the bonds are going to be broken. And again, just like before, I kept the substances side by side like they were on the reactant side. So sodium is next to fluorine, and hydrogen is next to chlorine. Here's what's going to happen in a double replacement reaction. The sodium and the hydrogen are going to switch places. So now we have hydrogen fluoride or hydrofluoric acid and sodium chloride. Notice that the atoms that we started with aren't bonded the same way that they were before. Now to finish this off, we're going to have a hydrogen fluoride molecule and a sodium chloride crystal. Here's what we started with. And then you can see what we ended with. Do you see how the elements switched partners so that now they're bonded differently than they were before? And we had two compounds that switched partners. That makes it a double replacement reaction. Here are some other examples of double replacement reactions. As you look at these reactions, you'll notice that the substances that were in the reactant side, compounds bonded together, have switched the atoms that they were bonded to. So on the product side, you have different combinations. Each substance swapped one of its elements with the other substance. So that's what makes a double replacement reaction. Now you know about two more reaction types: single replacement and double replacement. And these are decidedly more complicated reaction types than simple synthesis or decomposition. But it's important to understand them in understanding how real-world substances work, because these single replacement and double replacement reactions happen all the time in the real world. And to understand the chemical reactions that happen in the created universe, it's important for you to understand these different types of chemical reactions.